Vedete a tutto schermo?
Sì.
Sì, sì.
The title of this presentation is Hans Berger's Resting State EG Alpha Rims after a Centenary. And you can see here the main contributors of this presentation. Electroencephalographic rims were discovered by Hans Berger in 1924. The date of the first recording of human EG activity. Hans Berger was a German psychiatrist, and you can see in the picture the first EG recording system. Hans Berger was the first to term human electroencephalography and the first to term alpha and beta waves of electroencephalographic activity. The first recording was in 1924, but the results of these EG recordings were published in 1929. The intuition of Hans Berger was that EG could represent a probe to investigate the neural correlates of mental states. So vigilance, transition to sleep, and also cognition. And was the first to understand the importance of the recording of epileptiform activity by means of EG recordings in epilepsy patients. Hans Berger recorded EG activity in the resting state, eyes closed and eyes open conditions, and also during some cognitive tasks. The resting state, eyes closed and eyes open conditions are the most popular procedure to record electroencephalographic activity in a clinical environment. In the picture, you see a person who is psychophysically relaxed in a armchair, in a comfortable position. You can see the EG helmet with the scalp electrodes and some control sensors for recording electromyographic activity. And you see that the experimenter can follow the EG activity on a monitor of a computer. In the resting state condition, the participant is expected to keep the mind free from goal-directed actions, from goal-directed thinking. And so the resting state condition is ideal to investigate the EG activity during the transitions of vigilance from consciousness to drowsiness or light sleep. And also during longer recordings, also deep sleep. The vigilance regulation is an important function of the brain and brainstem. Is related to the functioning of ascending subcortical neuromodulatory systems the reticular formation of the brainstem, and the cholinergic nuclei of the forebrain, and also ascending systems from orexinergic and histaminergic systems from hypothalamus. Also important for the regulation of cortical arousal and vigilance is the thalamocortical interactions. We will see these in the next slides. In this picture, you see how we can frame the vigilance states and transitions in humans. You see that we have a graph with 2 dimensions. In the horizontal axis, we have the level of consciousness or level of vigilance. In the horizontal axis, we have content of consciousness or vividness of contents of mental representations. You see that the higher the level of consciousness, and the higher is the conscious experience from deep sleep, light sleep, drowsiness, and full alertness and full conscious experience. From left to right, you see that the measure of vividness of the contents of consciousness are the vividness of the mental representation of our thinking or mental imagery. And so we can say that the EEG activity is perfect to investigate the cortical activity related to the level of vigilance from deep sleep, light sleep, drowsiness, and conscious experience. And here we come back to the Hans Berger's EEG recording. You see that in the left, there is the electrode montage used for the first electroencephalographic recording by Hans Berger. And you see that we have 2 electrodes in a very simple 1 bipolar channel for EEG recording. You see that we have a positive and the negative electrodes placed in the frontal and in parietal scalp regions. The voltage recorded from this bipolar channel is amplified and then can be visualized by an oscilloscope or a modern computer. Hans Berger's used an oscilloscope. You see that in this photograph of the oscilloscope of Hans Berger, there is a phase of EEG activity related to eyes closed condition, resting state in green. And you see that in this bipolar EEG activity is very clear an ample oscillation of EEG activity. And in the bottom of the picture, you see an oscillation electronic oscillations at 10 Hz. And you see that this ample oscillation of EEG activity during eyes closed condition is very close to 10 cycles, 10 Hz. When the subject received the instruction to open the eye, you see in red, eyes open condition, you see that we have a reduction, a disappearance of the ample oscillation at 10 Hz. And instead of the ample oscillations at 10 Hz, you can see a small voltage, higher frequency EEG oscillations. In the bottom of the picture, you see that at a given time, Hans Berger asked again to close the eyes to the participant. And you see in the final part of the recording that the ample oscillation at about 10 Hz appeared again, to demonstrate that this ample oscillation of EEG activity at 10 Hz is strictly related to eyes closed, and so visual sensory deprivation. Based on these results, Hans Berger named alpha rhythms the ample oscillation at 10 Hz. And he related these ample oscillations to the idling state of mental activity during wakefulness, quiet vigilance. Hans Berger also turned beta rhythms from 20 to over 30 Hz and small voltages, the EEG activity appearing during the eyes open condition. This picture shows the cover page of the first publication of Hans Berger in a psychiatric journal, German psychiatric journal, Archive of Psychiatry. It's interesting that the first publication of EEG activity in humans by Hans Berger was the case at that time in neuroscience, in human neuroscience. And there was a hot debate about the nature of this electrophysiological signals recorded by Hans Berger. And some researchers stated that these electrophysiological signals were not due to brain activity, but they said that these activities were mainly artifacts. So Nobel Prize, Professor Adrian, after receiving the Nobel Prize for his fundamental research on single neuronal activity, decided to replicate the results of Hans Berger and recorded EEG activity with a system using 2 channels. And the results, here you see a recording with just 1 channel, and replicating exactly the montage of Hans Berger to replicate the Hans Berger's results. And you see that, the EEG recordings appeared very similar to those published by Hans Berger. In the Adrian's experiment, you see that there was the eyes closed condition in green, the eyes open condition, and also some visuospatial task based on watching a clock and saying the time indicated by the clock. So a typical visuospatial task. If you see during eyes closed condition, and you see that there was an ample oscillations at about 10 Hz. So you see in the right side of the picture, the time scale 1 second in this segment, and the amplitude in microvolt. And so Professor Adrian was able to replicate the recording of alpha rims at about 10 Hz during eyes closed resting state condition in quiet vigilance, and could also replicate the disappearance, the desynchronization of alpha rims during eyes open resting state condition, exactly the core finding by Hans Berger. And you see that in the recording, the alpha rims appeared again when the participant opened again the eyes. Interestingly, the alpha rims showed a reduction, desynchronization, even when the subject was involved in the visuospatial task. The results were published in 1934 and represented a very clear demonstration that EEG activity could be recorded from human scalp in a wakefulness condition. The EEG recordings were performed also by Professor Jasper in United States of America in 1935, the first publication that you see in the picture. Professor Jasper could replicate the Hans Berger's results, and you see that in the eyes closed condition, the alpha rims appear, and he could also demonstrate that EEG activity was affected by visual stimulation flashes. And he could demonstrate with this visual stimulation that even after the switching off of visual stimuli, there was a desynchronization of alpha rims, an appearance of beta rims after a few seconds showing that the desynchronization of alpha rims was related to both visual information processing, but also some mental elaboration of the visual flashes for a few seconds after the switch off of the stimulator. So this was the first demonstration that the alpha rims were desynchronized also in relation to a mental activity. Some visual imagery followed the visual stimulation. So the EEG recording was able to unveil not only the changes of brain activity during quiet vigilance, eyes closed, or visual information processing, eyes open condition, but also some relation with purely mental information processing. Some years after these fundamental discoveries on the human EEG, another smart scientist, Professor Hori from Japan, could show the fine changes in amplitude and frequency of ongoing EEG activity during the transition from eyes closed condition, quiet wakefulness, and you see in the top of the picture the ample alpha rims. You see in the bottom the time scale, 1 second in this segment, and 50 microvolt, the voltage of scalp EEG activity. And you see that the ample oscillation at 10 Hz, about 8 to 12 Hz in different subjects is related to resting state, eyes closed, quiet vigilance. But that there are, from the same channel of EEG recording, there is some changes in alpha rims. You see some decrease in amplitude, some desynchronization of alpha rims during the transition to drowsiness. And these changes from the same bipolar scalp montage, the changes of EEG are very clear, with a further reduction of alpha rims during the transition to light sleep. You see, for example, that in this transition, you have a fluttering of EEG activity from the same scalp bipolar electrode montage. And when the light sleep is even more evident from a behavioral point of view, with muscle atonia and some posture of the participant during the EEG recording, you see that this is associated with another change in the amplitude and frequency of EEG activity. And you see, indeed, that a slower frequency appears in the EEG oscillations. This is a band called theta rims from 4 to 7 Hz. And this activity is called ripples of EEG activity. And then you see that when the transition to sleep is greater and greater, other changes in the EEG activity can be found. And you see some vertex sharp electroencephalographic activity, some peaks, and then big peaks, key complexes, and also these bars of oscillations reminiscent of alpha rims, which are the spindles of the sleep, the light sleep. And so the key complexes and spindles of EEG are the very clear manifestations of a non-rapid eye movement sleep. And so you see in this picture with these Horry's stages of the transition from quiet vigilance to sleep, you see that just from one recording channel from the scalp, you can follow the fine changes of the vigilance in the transition to sleep. And so EEG activity, ongoing EEG activity, can represent a useful and informative neurophysiological biomarker of the vigilance regulation and brain arousal in humans. You see that until now, we have evaluated the EEG activity, the voltages recorded from the scalp, for example, from one bipolar recording channel, evaluating the frequency of the oscillations, the amplitude in the traces of EEG activity over time. And you see here a sketch of EEG activity at 9 Hertz within the alpha band from 8 to 12 Hertz for 1 second. But in the modern way to analyze EEG activity, this trace of EEG activity in the time domain is used as an input for the spectral analysis of EEG activity. In the spectral analysis, the power of the EEG oscillation, for example, at 9 Hertz, from the higher peak to the lowest peak, this amplitude is squared to obtain the power of EEG activity. And then is represented in this typical graph on the right side of the picture. You see that in the vertical axis, you have the microvolt square for all frequency bands that you can obtain from your recording. In this case, we have 9 Hertz, and we reported in this graph, in this diagram, called EEG power density spectrum, we reported the power of 9 Hz EEG oscillations. And you see a peak, and the magnitude of the peak informs you about the power of alpha rims in that electrode channel for the period of interest. This is the basic spectral analysis of EEG activity. In this slide, you see a better description of the spectral analysis of EEG activity. And you see in this simulated EEG delta plus alpha plus beta, you see a sketch of EEG activity in this mathematical simulation of EEG formed by only 3 elementary oscillations, sinusoidal oscillations at 1.55 Hz in the band of delta, at 8 Hz in the band of alpha, at 20 Hz in the band of beta. And when you sum this EEG activity, you can obtain a sketch of EEG activity. In the spectral analysis, you can estimate the amplitude and power of the single oscillations contributing to the recorded EEG activity. And this estimation is performed by fast Fourier transform, a very popular technique of spectral analysis of EEG activity. And you see that this technique, the fast Fourier transform, is able to measure the power of EEG activity, for example, in these 3 oscillations, and to report this in a power density spectrum of EEG activity for this electrode channel. And you see here, for example, for delta 1.5 Hz, this power in the graph, or from alpha, 8 Hz, and the power in this graph, and from beta, and you see the power in this graph. And so you see that for the single channel you used, you have an EEG power spectrum showing the peaks of the elementary oscillations in the EEG activity. This kind of graphs are also used to identify the frequency in the alpha band from 8 to 12 Hz, showing the higher power. And the frequency showing the higher power density of EEG activity from 8 to 12 Hz is called individual alpha frequency peak, which is used as a reference for the definition of subbands of alpha rims. In the modern EEG techniques, the spectral analysis is also applied to understand the mathematical and statistical interdependence between EEG oscillations in one recording channel, for example, a frontal bipolar recording channel, and a posterior or parietal bipolar electrodes recording channel. For example, you see in the picture a sketch of mathematical simulations of elementary oscillations in the EEG activity, for example, 1.5 Hz in the frontal bipolar channel in the delta band. The oscillations at 8 Hz from the frontal electrode, and an oscillation in the beta 20 Hz from the frontal bipolar channel. And the same is true for the parietal bipolar channel. You can estimate the single oscillations from the complex EEG activity. And again, you have 1.5 Hz, 8 Hz, and 20 Hz. So one hypothesis that you can test with the using the technique of spectral coherence analysis. One hypothesis is that from frontal and parietal electrodes, you record two EEG activities which are correlated each other. Two EEG activities that show some relationship between the phases of the oscillations. And this can be tested with the coherence analysis, which show this kind of phase relationship between two EEG activities. The coherence spectrum is composed by a vertical axis with values of coherence between the two EEG activities with values 0, no phase relationship, to 1, the maximum phase relationship between the two EEG activities. And then in the horizontal axis, you have the frequency bands you have in your EEG recording. In this case, we see 1.5 Hz in the delta band, and you see that the two EEG activities at 1.5 Hz recorded from frontal bipolar channel and parietal bipolar channel show the maximum coherence in the EEG coherence spectrum. In these simulations, also the oscillations of 8 Hz in the frontal and the parietal bipolar channels show the maximum phase relationship, 1. And the same is true for the oscillations at 20 Hz in the beta band. So you see that the technique of spectral analysis of coherence between two EEG activities from a pair of recording channels allows you to estimate the interdependence and model a possible functional connectivity between the cortical areas generating frontal EEG, and the cortical areas generating the parietal EEG activity. So the spectral coherence of two EEG activities can be used for formulating a hypothesis on functional cortical connectivity during the EEG recording, in this case, resting state EEG recording. Another important step of EEG research was the localization of the brain generators of scalp recorded EEG activity. And in this slide, you see the core finding and the core concept. You see in the slide that we have an electrode recording EEG activity, for example, in a EEG oscillations dominant at 9 Hertz in the alpha rhythms, for example, during resting state, eyes closed condition. Under the electrode, you see in brown the scalp. Under the skull with the dry part. And under the scalp, the meninges, subdural component of meninges, and the space with the cerebrospinal fluid, and then the pia mater. Under the meninges, you can find the cerebral cortex, and in the picture, we have 6 neurons of the cerebral cortex. But the picture only represented the cortical pyramidal neurons having the main dendrites perpendicular to the surface of the cerebral cortex. And you see that the pyramidal neurons are characterized by the typical body with the shape of a triangle in 2 dimensions, a main dendrite oriented perpendicular to the cortical surface, and the axons targeting the lower part of the cerebral cortex. You see in this picture that the dendrites of these 6 pyramidal neurons are nicely ordered in the space. In the picture, you can also see axons and the axon terminals, the green triangles, which establish synaptic contacts with the main dendrites. When you have the simultaneous neural transmission, you have simultaneous postsynaptic potentials at the level of the main dendrites of the cortical pyramidal neurons. And this spatial orientation of the dendrites, like a palisade, allows the spatial summation of the ionic currents and synaptic potentials when the transmission of neurotransmitters is simultaneous, synchronized in time. So when there is a synchronization in time of the neural transmission to these cortical pyramidal neurons, the ionic currents across the dendrites and related postsynaptic potentials are able to summate across the pyramidal neurons and reach the intensity of ionic currents and amplitude of electric field to allow the recording of EEG activity from scalp electrodes. So please take on mind the temporal synchronization of neural transmission to cortical pyramidal neurons, the synchronization in time, and the spatial summation of the ionic currents and postsynaptic potentials at the level of these dendrites as a main generator of EEG activity recorded from the scalp. And here in this picture, you see the nice relation between the spiking activity, the action potentials at the level of cortical pyramidal neurons in A, and in B, the amplitude of scalp recorded EEG activity. In A, in the upper part of the figure, you see the so-called roster of single neuron activity in which each dot is an action potential. You see that each line is the recording from one single cortical pyramidal neuron. And so you see that in the first part of the recording, the different neurons, the different lines show that action potentials, the dots, are not appearing at the same time, are not synchronized in time. And due to this asynchronization of neuronal activity and the different timing of action potentials across neurons, due to this fact, you see a flat EEG activity with a small voltage. But in the second part of the recording, in the right part of the picture, you see that the neurons, the pyramidal neurons in the cerebral cortex, show a synchronized activity reflected by the simultaneous appearance of action potentials. And so you see that these neurons are all active at the same time in a short period, and you see the train of action potentials for each neuron, and how this synchronization in time allows the generation of an ample EEG activity. You can see that after a period of intense bursting of action potentials in all these neurons, there was a silent period in which you cannot see any action potential in any neuron. And you see that this is related to the upper peak in this EEG recording. And after a short period, the neurons are again excited, and you can see the action potentials synchronized in a short period in these neurons. And this is related to the lower peak of EEG activity. And again, you have a silent period and the upper peak of EEG oscillation, and then another active period, and so on. So basically, this is the rhythmic activity of a neural population in the cerebral cortex. Rhythmic activity of cortical pyramidal neurons, determining the frequency and amplitude of EEG activity recorded at scalp level or by subdural electrodes, or even intracortical EEG recordings of local field potentials. So EEG activity is not a noise signal from the brain, but is strictly related to the rhythmic activity of large neural populations in cerebral cortex, especially cortical pyramidal neurons having spatially ordered main dendrites. And this neurophysiological index is able to show the frequency of the oscillatory activity of these neural populations. For example, in the theta frequency or alpha frequency or beta frequency. And the amplitude of EEG oscillation at a given frequency can represent a model of the amount of synchronization across neurons in a given cortical region. So this is very specific. EEG activity doesn't reflect the activity of all neurons in the cerebral cortex, but specifically for cortical pyramidal neurons, and not in the activity per se, because you see that in the first part of the recording, you have a lot of action potentials, a lot of neural activity, but the lack of temporal synchronization of this activity across cortical neurons, the lack of synchronization doesn't allow to record EEG activity with ample peaks. So it's not a matter of activity per se of the cortical neurons, but the rhythmic activity of the cortical pyramidal neurons. Here we have a slide of Vincenzo Brunelli, our scientist working in Scotland. And he gave very important contributions to understand the generators of EEG activity during wakefulness and sleep by means of recordings of action potentials and postsynaptic potentials at the level of single neurons in the cerebral cortex and in the thalamus. In this slide, you see in the left a model of the cerebral cortex, and you can recognize the cortical pyramidal neurons with the main dendrites targeting the surface of the cortex. In green and blue, you see thalamic nuclei. In green, nucleus reticularis thalami, which is populated by neurons from reticular formation in the thalamus. And in blue, the thalamic relay nucleus of lateral geniculate nucleus, which is the visual sensory thalamic nucleus. And you see that there are some connections from pyramidal neurons, and the axons target the neurons in the nucleus reticularis thalami, and also the thalamic neurons in the visual relay nucleus of the thalamus. You see that we have thalamo-cortical neurons from the thalamic relay nucleus with the axons targeting cortical pyramidal neurons. And also the neurons of the nucleus reticularis of thalamus. You see that in this nice picture, you can see the cortical pyramidal neurons use an excitatory neurotransmitter glutamate to excite the reticular thalamic neurons and the thalamocortical neurons. Along the same line, thalamocortical neurons target cortical pyramidal neurons with an excitatory neurotransmitter glutamate, and also release glutamate excitatory in the nucleus reticularis thalami. In contrast, the neurons in the nucleus reticularis thalami release inhibitory neurotransmitter GABA to the thalamocortical neurons. And so Vincenzo Brunelli's group was able to demonstrate the connectivity between the cortical pyramidal neurons and the thalamic nuclei, the release of neurotransmitters, and the relation between this connectivity and the generation of local field potentials at the frequency of alpha rims, alpha waves. He could obtain this neurophysiological model from in vitro recordings of action potentials and local field potentials from tissues, including cortical and thalamic neurons, but also by in vivo recordings from mice, cats. In this case, you see results from recordings from visual cortex and thalamus of cats during relaxed wakefulness in the animals. And you see that from occipital cortex, he could record a clear alpha rhythm. You see in bottom the time scale 500 milliseconds in this segment, and the amplitude 50 microvolt. And you see the alpha rhythms from occipital cortex, the visual cortex, and a very similar oscillatory activity dominant at about 10 Hz from the nucleus of the sensory thalamus, lateral geniculate nucleus. And when you compute the power density spectrum from the EG local field potentials from the occipital cortex and the lateral geniculate nucleus, there is a difference between electroencephalographic activity and the local field potentials, which is related to the dimension of the electrodes, recording electrodes. If you use a relatively large electrode, for example, a metal disc over the skull, you will record EEG activity because you are recording from a relatively large surface of the skull. If you use a thin electrode with a small pin from the skull or from the cerebral cortex, you will record local field potentials, which are related to a smaller number of neurons. You see here that in red, you have the power density spectrum from this signal recorded from occipital cortex with local field potentials. And you see that the maximum power is recorded at about 10 Hz. Under the power density spectrum, there is a graph showing the cross correlation between the local field potential from occipital cortex and lateral geniculate nucleus. And you see that the higher correlation, almost perfect correlation, is observed in signals at the same phase without any time shift. And this means that the two local field potentials from occipital cortex and lateral geniculate nucleus was highly correlated showing this kind of functional connectivity from thalamus to cerebral cortex and from cerebral cortex to thalamus. And this was a very nice demonstration of the cortical loop, the functional connectivity between thalamus and cerebral cortex in the generation of alpha rhythms in the brain of cats. You see the symbol of red to emphasize that an ample EEG activity is related to quiet vigilance, relaxed wakefulness. So it's a sort of stop of intense information processing. This is another nice finding from Corneli's group, showing again the strict relationship between the synchronized activity of single neurons in the thalamus and local field potentials in the alpha frequencies. He could demonstrate that the thalamic neurons show a rhythmic, a part of thalamic neurons he called high threshold thalamocortical neurons, show a synchronized rhythmic activity. In short periods, you can see trains of action potentials. After a while, a silent without action potentials, and then again a short period of high trains of action potentials and so on. So a very clear rhythmic activity of these high threshold thalamocortical neurons, and in strict relation with the periods of high intense activity of these neurons, you have the peaks of local field potentials at alpha frequency. And so you see that in this specific case, you have a clear relation between intense spiking activity of thalamocortical neurons and the upper peak of the oscillation of local field potentials. And the silent period is related to the lower peak of these oscillations, and so on. So we gain information about the generation of EEG alpha rhythms from these studies. And this is another important scientist in the field of EEG, is Fernando Lopes da Silva. Is a Portuguese scientist working for many years in the Netherlands, and able to give important contribution on the fundamental research on EEG alpha rhythms. In this particular publication of Fernando Lopes da Silva's group, you see that he used electrodes penetrating across the cerebral cortex, the visual cortex of dogs. And you see in the left side of the figure, in black, the recording contacts of the stick electrodes. And you see that across the layers of the cerebral cortex, you can record EEG activity. And you see that the upper peaks in the surface layers are strictly related to the lower peaks in the lower cortical layers. So there is an opposite polarity of EG activity in the surface and in the deep of the cerebral cortex. And this demonstration showed that the generator of this alpha EG activity is localized halfway the surface and the deeper cortical layers. And you see here the approximative level of the generators of cortical alpha rhythms from the visual cortex of dogs. And this opposite polarity of EG activity in the surface and deep cortical layers confirms the dipolar two poles, the dipolar nature of the generators of alpha rhythms in the cerebral cortex. Professor Fernando Lopes da Silva was also able to record local field potentials and EG activity from animals, behaving animals, dogs, in this particular research. And you see two electrodes in the visual cortex of dogs, electrode 10 and electrode 9. And during the same recording, he was able to record from lateral geniculate nucleus, the visual sensory thalamus. This is a recording quite similar to that of Professor Vincenzo Crunelli showed in a previous slide. And again, you see the time segment in the 1 second in the bottom of the figure. And the vertical segment showing the amplitude 100 microvolt in these recordings. So you see an alpha dominant rhythm in relaxed wakefulness of dogs from recordings of in the visual cortex, electrode 10. The same is true for electrode 9. And like the previous slide of Crunelli's work, you see that you have a very clear alpha oscillation even from lateral geniculate nucleus, the visual sensory thalamus. In the right part of the picture, you see the power density spectra obtained from electrode 10 visual cortex, and it's very clear that even if the EG activity is complex, the dominant power density is observed at 10 Hz. From the lateral geniculate nucleus, you see again a dominant power density peak at 10 Hz, like the visual cortex electrode 10. And the same is true for the electrode 9 of visual cortex. Again, dominant power density peak in the power density spectrum at 10 Hz. In the right part of the picture, you see also the coherence spectra. And the coherence spectra showed the phase relationship between EEG activities in between two electrodes in the upper case from electrode 10 and electrode 9 from visual cortex. And you see that there is a very high spectral coherence between the EEG activity in the electrode 10 and 9. And so Professor Lopes da Silva concluded that the higher level of functional connectivity related to alpha rims, cortical alpha rims, is due to cortical connectivity. But also the results of spectral coherence between electrode 10 and the lateral geniculate nucleus show a very clear peak of coherence at 10 Hz between the electrophysiological activity from electrode 10 and lateral geniculate nucleus. And so Lopes da Silva could show that cortical e.g. alpha rims or local field potential from intracortical recordings is strictly related to functional cortical connectivity, mainly, but also for some part from thalamo-cortical and cortical-thalamic functional connectivity. Professor Fernando Lopes da Silva was also able to show the strict relation between thalamocortical interactions and alpha rims in humans. In humans, his group used simultaneous recordings of resting state EEG activity during eyes closed condition and bold signal of resting state functional magnetic resonance imaging. So a co-registration of these two modalities during resting state in healthy humans. And you see the results in this picture. You see that in the magnetic resonance imaging, the bold signal indicating the ratio between oxygenated blood and deoxygenated blood, particularly oxygenate hemoglobin in blood red cells and deoxygenate hemoglobin into the red cells. This ratio is represented in the bold signal recorded during functional magnetic resonance imaging scanning. And you see that in this magnetic resonance imaging, in gray, you have the results of structural volumetric sequences. And in color, in blue and the red, you have the representation of the bold signal of the functional magnetic resonance imaging. Red means high bold signal. Blue and black indicate low bold signal. And so you see that there is, in this case, a high bold signal in parieto-occipital cortical areas, which is related to flat EEG activity, low alpha rims from 8 to 13 Hz. So this is another demonstration important from humans that high posterior cortical activity is related to desynchronized alpha rims with low amplitude. In contrast, there is an ample alpha rims in relation to low amplitude of bold signal in the resting state functional magnetic resonance imaging. So this means that when there is low cortical activity as revealed by bold signal, there is an increase of amplitude of alpha rims. This is why I put red in this symbol. Stop to cortical information processing with ample alpha rims in relaxed wakefulness, quiet vigilance. In contrast, higher levels of bold activity in the thalamus is related to high levels of EG alpha rims in the scalp recordings. This means that the thalamus is very active to modulate cortical neural activity. And the thalamus is able to inhibit cortical pyramidal neurons generating alpha rims. In this slide, we see another interesting result more recently. The researchers used high-resolution EEG recordings from human scalp in healthy subjects and use an estimation of cortical source activity with some mathematical software, some mathematical model represented in freeware software, and were able to apply a principal component analysis of source activity explaining alpha rims. And they were able to distinguish two components in the source space, explaining the resting state alpha rims at eyes closed. And you see the two components called ARC1, ARC2. ARC1 in green is characterized by 11 Hz and the cortical source activity in this occipitoparietal green sources in the model. And this is the typical so-called dorsal where-how visual stream, allowing us to transform the visual stimuli in a visual spatial representation of the objects, for example, and to integrate our motor planning with the visual spatial frame to allow the proper motor commands to go towards the objects in the space. In red, you see that the component ARC2 shows a lower alpha frequency peak at about 9 Hz, and also a lower power density. This component is related to source activity in these occipital temporal cortical sources in red, in the brain cerebral cortex model. You see here the basal occipital temporal lobe, here the lateral occipitotemporal lobe of the two hemispheres. And this is the typical pathway of the so-called ventral word visual stream, allowing us to classify the visual objects according to semantics, visual features. So the alpha rims in the resting state condition at eyes closed as mainly related to visual spatial and ventral visual stream pathways in the cerebral cortex. And they mainly reflect the parietal occipital and occipital temporal visual transformation pathways. But this dominance of visual alpha rims should be considered together another important source of scalp recorded EEG alpha rims, the primary sensory motor cortex in the precentral and postcentral gyri of the cerebral cortex, and also the frontal premotor cortex. So there is also another component of alpha rims in the EEG activity, the so-called mu rhythm, motor alpha rhythm, better somatosensory motor alpha rhythm. So these are the visual alpha rims, and the somatomotor alpha rims are the two main components of alpha rims. Another component of alpha rims is the third alpha rhythm, is related to associative temporal cortex, and is mainly related to ARC2 components in the publication of these authors. The next slide will show the informative input that we can gain from EEG alpha rhythms on the regulation of vigilance and consciousness levels. This slide presents the results of a study in which the experimenters use a sleep deprivation of 1 night in healthy volunteers. The design included 1 resting state, eyes closed, EEG recording before 1 night of sleep deprivation, and the EEG recording in the resting state condition after 1 night of sleep deprivation. So in the slide, you see pre-sleep deprivation, before 1 night of sleep deprivation, and in red, post-sleep deprivation, immediately after 1 night of sleep deprivation, in the same group of healthy volunteers. And here you see the typical representation of results in this presentation. You see that in the vertical axis, you have the cortical source activation estimated by a free software called Iloreta, which is the mathematical way to estimate the currents in the cortical sources from scalp recorded resting state EEG activity. And you see that in the horizontal axis, you have the frequency bands, delta, theta, alpha low frequency, alpha low frequency 2, alpha high frequency, or alpha 2, beta low frequency or beta 1, beta high frequency or beta 2, and gamma. And you see that we have also cortical regions of interest, frontal, central, which means precentral and postcentral or Rolandic, and parietal, occipital, temporal, and the midline limbic cortical structures according to the brain model of Iloreta software. And you see in blue, before sleep deprivation in these healthy volunteers, you see that the maximum cortical source activity was estimated in low frequency alpha or alpha 1 in parietal source. Also in occipital source, you see high level of cortical activity in low frequency alpha or alpha 1. what happened after one night of sleep deprivation? We observed a clear reduction of source activity in the same condition of resting state, eyes closed, quiet, vigilance, relaxed wakefulness. In other words, even if from a behavioral point of view, we have a relaxed wakefulness, and you see that there is a different source activity in posterior alpha solutions. So we can conclude that alpha RINs are sensitive to the decrease of quiet vigilance after one night of sleep deprivation. And this put in relation the intensity of the activation in alpha source activity in parietal and occipital especially, but also you see in other sources. And that this sensitivity of alpha source activity in parietal occipital sources represent a resource for using a neurophysiological correlates biomarker of vigilance regulation in humans. Again, I use red symbol in this picture to indicate that ample alpha source activity in parietal occipital areas are related to the inhibition of cortical information processing of visual contents. And these results are related to another demonstration of the relation between alpha source activity in the resting state, eyes closed, to the vigilance level. In this picture, we reported the results of an experiment on a group of normal elderly participants and old in blue, and one group of patients with mild cognitive impairment due to a neurodegenerative disease during aging, the Alzheimer's disease, AD. But put your attention to the blue group, the healthy, normal, elderly subjects. You see that we have 4 columns here, which are related to the conditions of ongoing EEG recording. In the first column, we have the eyes closed resting state condition. In the second column, we have again a resting state eyes closed condition, but after 15 minutes of recording. In the third column, we have a period of the recording, about after 40 minutes, in which we see the fluttering of EEG alpha activity. And in the fourth column, about 50 minutes recording, we see that we have the signs of ripples of increase of delta and theta activity in relation to light sleep. You see that in the right side of the picture, again, the Horace stage of the changes of EEG activity, ongoing EEG activity, from the quiet wakefulness with alpha waves to reduction of quiet vigilance, lowering of brain arousal with lower alpha rhythms, less amplitude, and some fluttering. And then again, longer tracks of fluttering in the EG recording with the transition to drowsiness and the first stage of sleep with the fluttering and the ripples. And so we divided in these periods our long EG recording, and so put attention on, in blue, in frontal source regions, parietal source regions, and occipital source regions. And you see that in the resting state condition, the first column is eyes open condition, eyes open, resting state, eyes open, which means the desynchronization of alpha rhythms. And indeed, you see that the frontal, parietal, occipital regions, so if you see the blue group of healthy normal subjects, you see that the dominant rhythm is in delta and theta, with low alpha rhythms related to eyes open and visual information processing. If you see in the period of eyes closed and so quiet wakefulness condition, you see that alpha increased in occipital areas. So you see the maximum level in the blue healthy group in alpha 2 and alpha 3 frequencies. And you see that you have also high level of alpha in relation to delta and theta in the parietal source, and decrease of alpha in the frontal leads. So a posterior dominance compatible with the visual and visual spatial pathways of visual information processing. If you see in the period of drowsiness, the fluttering of G, drowsiness and light sleep, you see that there is again a decrease of alpha, which is very sensitive to this decrease of vigilance. And the same is true for occipital, the blue line, and also parietal, the blue line. And even in the frontal sources. When we go to the last part of the recording with the ripples, you see that alpha is even lower in the occipital areas, and there is a clear increase in delta and theta, which became dominant in the posterior areas, and the same is true for parietal and frontal. So this is a nice demonstration that in a healthy subjects, the blue group, you have changes in the alpha source activity in the posterior areas, mainly parietal and occipital, in relation to the level of vigilance. When the vigilance is moderate with eyes open, with visual information processing, you have desynchronization of alpha in the occipital and parietal mainly. When there is eyes closed and so cortical inhibition in the visual system, you have an increase of alpha in the parietal and occipital sources. When there is drowsiness and a transition to light sleep, you have the fluttering of alpha activity, reduction in amplitude in the parietal and occipital sources. And then when there is a transition to light sleep with ripples in the EG, you see the increase of delta and theta. So the resting state EEG biomarkers are sensitive to the level of vigilance and can be used as a biomarker, neurophysiological biomarker of the vigilance regulation in humans. So you can use probably also for patients with brain diseases to probe the functionality of the brain ascending systems regulating brain arousal and vigilance levels. In this experiment, particular experiment of my group, we also tested the difference in the transition from quiet vigilance to light sleep in this long EEG recording diurnal during late morning, and also in the group of Alzheimer's disease patients with microcognitive impairment. And you see that these patients are characterized by a high level of delta and theta source activity in practically all conditions of wakefulness, fluttering, and ripples, and are also characterized by lower alpha source activity during wakefulness, quiet wakefulness, resting state, eyes closed. You see here. So this EEG biomarker can be used also to probe the dysfunction in the vigilance regulation in Alzheimer's disease patients with mild cognitive impairment. And now we move to the impact of vigilance regulation as revealed by alpha EEG rhythms on visual primary consciousness. Visual primary consciousness means the consciousness of a visual stimulus. And we tested the impact of pre-stimulus alpha rhythms on the primary consciousness of visual spatial stimuli. The task was is represented in the left part of the picture. One trial started with the cue visual stimulus. It was a visual spatial stimulus, a white circle, which could appear in the left or right part of the screen. The duration of this visual spatial stimulus was calibrated at individual level at the so-called sensory threshold, visual sensory threshold, so that the participant could be conscious of the left or right presentation of the cue only 50% of the trials, of the events. The sensory threshold was established in a preliminary phase of the experiment. After the presentation of the visual stimulus in the left or right side of the screen, there was a masked visual stimulus. There was 2x. After about 2 seconds from the cue stimulus, there was the appearance of the go stimulus. a green circle appearing for 500 of milliseconds, alpha second. This was sufficiently long to be always perceived consciously. In the instruction, we explained to the participants, healthy volunteers, to press a button, right button, if the go stimulus was on the right side of the screen, left button if the green circle was on the left part of the screen. After the hand movement on the button, we ask if the subject was able to see the cue stimulus on the left or right side. And he could answer yes or not. Yes means seen cue stimulus. No means not seen cue stimulus. So the reaction time to go stimulus allowed us to measure the attention to the task. Furthermore, we could also establish the elaboration of the cue stimulus, even in the not seen cue stimulus trials, because we could see the influence of the side of the cue stimulus on the reaction time to go stimulus in different sides to cue stimulus or on the same side of the cue stimulus. So we could control the behavior and the level of attention. Then we divided the trials in EG trials related to not seen cue stimulus and EG trials related to seen cue stimulus. We estimated the alpha source activity in blue. And you see in blue the spots of source activity generating alpha rhythms. And so it's very clear that the alpha rhythms in the where visuospatial pathway from occipital regions, Brodmann area 19, parietal, posterior parietal in Brodmann area 7, and also in premotor areas. In this visuospatial pathway or dorsal stream, we have higher source activity in alpha rhythms in the seeing cue stimulus rather than not seen cue stimuli. And so we concluded that high in the fluctuation of alpha source activity before cue stimuli, in the case of higher alpha source activity in the dorsal visuospatial pathway, there was more ability to recognize the side of the cue stimulus. So visual primary consciousness of spatial features of the cue stimulus was more frequent when in the trial there was high alpha source activity in the dorsal pathway before the appearance of the cue stimulus. In the same experiment, we wanted to demonstrate the causal effect of broadband area 7 in the posterior parietal cortex in the visual primary consciousness. So the area showing high generation of alpha rings during the scene cue stimulus trials. So to interfere with this parietal area, we use transcranial magnetic stimulation. In the picture, you see the coil generating a magnetic field that interferes with the activity of Brodmann area 7. We give this interference, magnetic interference in the Brodmann area 7 during the task, the same task of the EEG recording. And the hypothesis was that the parietal Brodmann area 7 generating a high alpha rhythm in the scene cue stimulus trials could be affected by transcranial magnetic stimulation and could produce a reduction in the number of cue stimuli perceived consciously. And you see here the results of the experiment. You see that in the graph, we have the number of seen cue stimuli in the block of 40 stimuli. In the red horizontal line, we have the number of cue stimuli perceived consciously with no transcranial magnetic stimulation. And you see that they are about 22 out of 40. And this was expected in relation to the use of sensory threshold for the appearance of cue stimuli. In yellow, you have the number at the group level and the standard error, the dispersion bar. You see the number, the mean number of cue stimuli perceived consciously during a fake stimulation with the coil. So the coil was put on the head and there was a sound, but no magnetic stimulation. And you see that we have almost the same number of cue stimuli perceived than the no transcranial magnetic stimulation, about 21. When you see the violet and blue, you see that the results of the effective transcranial magnetic stimulation to interfere to right parietal area, Brodmann area 7, and the left parietal area, Brodmann area 7 in the left side, left hemisphere. And you see that there was a small but statistically significant reduction of cue stimuli perceived consciously after the interference with transcranial magnetic stimulation, showing that this area plays an effective role in the primary consciousness of the visual spatial features of visual stimuli.